Okay, so yeah, so this is where we stand currently in this three-part tutorial. The first part yesterday we discussed game theoretic testing, and today we're going to discuss game theoretic estimation, and then today afternoon we'll discuss game theoretic change detection. Since maybe not everyone was there yesterday, there are some key points I want to recap, so I'm going to spend 5 minutes on a recap of what we discussed yesterday, and then move to the estimation problem. Okay. So here's a quick recap of game theoretic testing. We saw it was connected. Gambling and betting are connected fundamentally to many areas, but the ones we explored yesterday were the connection to information theory and statistics simultaneously. The core idea was testing by betting, and we said in order to test a null hypothesis, we're going to set up a game which has two properties. If the null hypothesis is true, then no strategy can systematically make money. In other words, its wealth is a non-negative super martingale. But if the null is false, then there exists a good betting strategy that can make money. Okay, so that's the core idea of testing by betting. I give you a hypothesis testing problem, and you say, I'm going to transform it into a game, and this game is going to have two properties. So the wealth, maybe we close the door. So the wealth in the game is directly a measure of evidence against the null. And every strategy of the statistician in this game corresponds to a different estimator or test statistics. And we saw that there are good and bad strategies for betting, just like there are good and bad estimators or test statistics. And so we changed the problem of testing and estimation to one of game and strategy design. Okay, so that's what we saw yesterday. And one of the core definitions, which maybe we'll come back today, is the definition of an E-value or an E-process. If I have a composite null hypothesis and E-value, so E-value was the fact that under any distribution in the null, so let's call E an E-value if the expected value of E is less than or equal to 1 for every distribution in my null hypothesis, and an E-process was a sequential version of this. This is a super important definition. So an E-process is a sequence of E-values such that at any stopping time, the expected value of E tau is less than or equal to 1 for all P in the null, and for all stopping times, and for all stopping times tau. So that's this E-process is a key central concept, and examples, we saw examples of E-processes which are like non-negative martingales, non-negative super martingales, but the key part is that for composite null hypotheses, which are non-parametric and may not have a reference measure, we can still construct these type of general non-negative martingales and super martingales. Okay, so these definitions I've just written here so that you have them for later. And then a summary of yesterday's talk was that testing by betting is a simple framework for hypothesis testing that yields this kind of sequential and anytime valid inference. That's, you can continuously monitor your data, stop at any arbitrary stopping time, and you have valid inference. Optimal gambling strategies, which was the second half of the talk yesterday, we saw that optimal gambling strategies are based on likelihood ratios. Composite alternatives can be handled using mixtures or hedging, but composite nulls are handled using this idea of what's called a reverse information projection, or via universal inference. I didn't discuss this. I might come back to it later today, but you can take maximum likelihood under the null as well. Okay, and we saw this fact that composite non-negative super martingales are actually secretly likelihood ratios. We might have composite nulls which don't have a reference measure, and we saw several examples yesterday where there's no reference measure, like symmetric distributions, sub-Gaussian distributions, bounded distributions, things like that, where you can't even begin to define likelihood ratios, but no problem, non-negative super martingales exist, and they work exactly like proxies for likelihood ratios, and so they're like simultaneous likelihood ratios, and so that was a really key advance. And this idea of the E-process is even more general. E-processes exist even more generally, even when non-negative super martingales don't exist, and they are the central objects that are necessary and sufficient for sequential testing. Okay, so this was a very quick summary of 5-minute summary of yesterday's talk. For those of you who were here, hopefully it just refreshes your memory a bit. For those of you who weren't here, I hope at least some key definitions are up here that will be useful later. Okay, so now we said, okay, we understand reasonably at least some like how to do game theoretic testing. So now what about estimation? How can we think about estimation in this framework? So I'm going to start again, like yesterday we started with a simple example first, this coffee taste, example, and then we went more abstract later on. We'll do the same thing in today's talk. I'll start with a very simple problem. And then in the second half of the talk, it's going to get more abstract and complex. Okay, so this non-trivial, non-parametric example I'll start off with is from a JRSSB discussion paper we had last year with my student Ian Wadby Smith. And the title of the paper is Estimating Means of Bounded Random Variables by Betting. So it's a very simple problem. Let me state the problem for you. It's super simple. So let x1, x2 and so on, think of the IID case. There's no problem. This does not need to be IID, but it's helpful if you think about the IID case to keep things simple. So let's say you have IID random variables from a distribution on 0, 1, and the mean is mu. Okay. So the first question is, how can we construct a confidence interval for mu? Okay, simple. And the second one, which I will come to because I haven't defined it yet, but the question is going to be, how can we construct a confidence sequence for mu? So this is an old problem going back 60 years. The first answer given by Hoofding in about in a JASA paper in 1963 said that, what's now called Hoofding's inequality, but what it effectively boils down to is saying that you take a confidence interval which is of the form sample mean plus or minus square root of log 2 over alpha by 2n. Alpha is the level of the confidence interval, so you want a 1 minus alpha confidence interval, and n is the sample size in this case. And so he says, well, this is a reasonable scaling. It's like 1 over root n width, that's reasonable. The dependence on alpha is logarithmic, reasonable. So this seems like a reasonable answer, but it's actually not a good answer because the second term does not depend on the variance of the data. So somehow, whether your data is low variance or high variance, the width is exactly the same, and so it's a conservative confidence interval, but it's actually not a very good one. So people recognize that, and then they came up with what are called empirical Bernstein confidence intervals. This particular one is from Maurer and Pontil around 2009. So they had I think maybe an ICML paper or something like that, in which they derived a very simple empirical Bernstein inequality. The key thing to note over here is that now it has two terms. The second term is of lower order, so it's now it's like 1 over n, and so it should be smaller for large enough n than the first term, but the first term now has an empirical variance in there. So the empirical variance of the data is small, you're going to get a smaller width, and this is a non-asymptotically valid confidence interval, and yeah, so it should typically be better than this, at least for large enough sample sizes. But the key part that we're going to see, we'll see in a lot of simulations now, that instead if you do betting, you're going to do much better than these answers. So empirically and theoretically you can prove that you're going to significantly outperform these if you take a betting perspective. Okay, so that's what we're going to see, but hopefully at least if you haven't seen these other simple answers before, it's okay, you can just forget about them, and we'll just show you how to solve this problem by betting. It will turn out that betting is naturally sequential in nature, so what we're going to get is actually a confidence sequence for mu. So let me define what a confidence sequence is. So a confidence sequence is the natural sequential analog of a confidence interval. Okay, so a confidence sequence for a parameter theta is a sequence of confidence intervals ln un that are constructed from the first n sample sizes. So just the subscript there is the sample size or the time. And now this confidence sequence has a uniform or simultaneous coverage guarantee over all sample sizes. So essentially the difference from a confidence interval is now you say the probability that for all t simultaneously theta lies in LTUT, that probability is at least 1 minus alpha. So this definition goes back to Darling and Robbins, where mostly Robbins and his collaborators in the late 60s and early 70s, Lai and Siegmund and stuff like that, and kind of lost popularity for about 30-40 years, and then now the bandit community in machine learning has really brought this back into focus, because it turns out that to derive regret minimization algorithms or best time identification algorithms, confidence sequences are a key building block, and so it's for many sequential learning problems this notion is key. This is much stronger than the pointwise fixed sample confidence interval guarantee that you learn in statistics, where the for all quantification is outside the probability. Okay, so that's what when you say I have a confidence interval, this is what it really means. For every fixed sample size, it has a 1 minus alpha guarantee. It's definitely not simultaneous over sample sizes. There's many other ways of defining a confidence sequence. So an equivalent definition actually is in fact, the equivalent motivation for a confidence sequence is that you should not this idea that you don't want to contradict yourself in the future. Okay, so let me explain this notion, because it's just it's a simple motivation. It turns out that when you construct a confidence interval, like at some particular sample size, I'll ask you the question, what's the probability that if I ask you to construct more confidence intervals in the future, that you will contradict yourself. What does it mean to contradict yourself? It means now you say 0.1 to 0.2 is the answer, and then later on you say minus 0.1 to minus 0.2 is the answer. It's completely, there's no overlap between your answers. Turns out that with confidence intervals, this will happen with probability 1. In every single sequence of observations that you draw, you will contradict yourself if you're producing confidence. You know that. Even when you produce one confidence interval, you already know that you will contradict yourself in the future. And the reason behind this is something called the law of the iterative logarithm, is because most of these confidence intervals you're going to look at, I'm going to have 1 over root n width, but the law of the iterative logarithm says your random walk is going to have square root log n by n deviations. And so you will so when you produce a confidence interval, you already know that you're going to contradict yourself in the future. So it would be nice if your confidence interval ln un is not contradicted by a future one you produce lm um for any m greater than n. Okay, and it turns out that that's an equivalent motivation or definition of a confidence sequence. For pointwise confidence intervals, the intersection of all the confidence intervals you produce is going to be empty almost surely in every run of the data. But with confidence sequences, the intersection of all the answers you produce is actually going to be the truth theta with high probability, with probability at least 1 minus alpha. So this is like a different motivation of not wanting to contradict yourself. It seems like a reasonable philosophical motivation. And the part that's going to connect to what we called sequential anytime valid inference yesterday was the fact that this is actually another definition of a confidence sequence, which is that for any stopping time tau, the probability that theta is not in L tau U tau is at most alpha. There's no restriction on the stopping time here. It could be potentially infinite, it could be anything. But the idea is that no matter how you stop, your probability of miscoverage is at most alpha. Yeah, I mean, I've written coverage over here, I'm writing miscoverage over here, but you can go back and forth between the two. But this is actually an equivalent definition, meaning these imply each other. If you define a property like this, it implies this one, and if you define this one, it implies the other one. So it's but all of these could be thought of as definitions or motivations for confidence sequences. I would like to be able to track my data, stop at any time, and have a valid inference at the stopping time, and then you're asking for a confidence sequence. Okay, so hopefully this definition is clear. I mean, I won't write it down. It's just there's a for all on this side, so hopefully it's simple enough. Okay, so as I said, there's many ways of writing this definition. So if you want to flip the for all to an exists with a miscoverage. So this is saying coverage for all. This is saying probability that there exists any n at which I miscover is at most alpha. You can write this as a union bound, as an infinite union bound over an uncountable number of events, saying that the union over n of this event is at most alpha. And more generally, there's no reason that you need to start at time 1 or something. You can say, well, maybe there's an initial sample size n0 that I want this coverage after, that's fine. Your theta need not actually be fixed. Theta itself could be a parameter that varies with time, and there's many situations where that happens, and you can ask for theta n, and there's no reason it has to be intervals. And more generally, it could be a confidence set that's multivariate and things of that kind, that's fine. And you can ask only to peak at particular times, saying I don't want to peak at every time, I want to peak only at certain geometric epochs, that's also fine. So like you can get into variants of the definition. I'm going to, for simplicity, not tell you about these numbers to subscript, superscript to track, and our definition is going to just be that definition of a confidence sequence. And I said some implications are you get valid inference at arbitrary stopping times. You actually also get post hoc inference in hindsight. So for any random time t that's not a stopping time, you actually still get a valid confidence interval. So suppose you're running a sequential experiment and you stop at time 120, and then your boss asks you, why did you not stop at half the stopping time? Why did you not stop at time 60? Time 60 is not a stopping time, it's a random time. It's half the stopping time, which is not a stopping time. But you can say, well, this was the confidence interval at time 60. It's actually a valid confidence interval at time 60, and it was not good enough for me to stop, and whatever. You can have valid post hoc inference. And there's no pre-specified sample sizes, so which means you can stop early or you can extend experiments later on. You can do whatever you want, and none of this can violate the validity. So it's very useful for settings where you don't know what kind of signal strength you're looking for, you don't know what's the sample size you really need. Maybe you start off planning for 200 samples. When you reach 200 samples, you realize it's not enough. Fine, collect 50 more samples, no problem. So you can do whatever you want, and it's a very clean, allows this kind of clean, flexible stopping time guarantee. And these actually all imply each other, which means if you want any of these, you have to get all of them. So these are equivalent definitions of a confidence sequence. Okay, so that's a confidence sequence. So let's return to our problem, which was I have a IID random variables from a distribution on 0, 1. How do I construct a confidence interval or a confidence sequence? This seems like a statistical problem. Where is the game, right? Like, so I mean, I have an estimation problem. Where's the game in all this? Okay, so what we're going to do is we're going to, like we did yesterday for several problems, we're going to convert this problem to a game, and this is how the game is going to work. So you're not going to play one game. It turns out that for estimation, you should think about estimation as playing a family of games. Okay, and so the games are going to be indexed by m, which is in the range 0 to 1. You should think of m as being a hypothetical possible answer for the true mean. So the true mean is going to be called mu, and mu is anything in 0, 1, and so m is like an index for possible means. And in each of these games, you're going to start off with $1. Okay, so K0, K is for capital. If you're German, then Kapital, it's like that, that's why K. And the subscript is the time of the game. So at time 0, in the mth game, you start off with $1. Okay, and at each time from 1, 2 onwards, this is what you do. The statistician is going to declare, in every game, he's going to declare a bet. Okay, and this bet is something in the range. There's some range. You should think of this as -1 to 1 for simplicity, but I'll tell you why this weird range comes up. It's very simple, but anyway, you declare a bet, let's say in -1 to 1, okay, and in every game, and then reality reveals xt, and then your wealth in the mth game gets updated in the following manner. That is, in the mth game, your capital after t steps is your capital after t minus 1 steps multiplied by this. This is the multiplicative factor for that game. It's 1 plus lambda t times xt minus m. Okay, so xt is given by reality, m is the mth game that I'm playing, and this lambda t is my bet. That's the bet that I made. Okay, so the reason that lambda t lies in this weird range is just to ensure that this is non-negative. Okay, so xt lies in the range 0 to 1. So when it's 0, it can take on the value minus m. So if it's this, that's why 1 over m. And when it's 1, it's 1 minus m. So that's why this end. And so essentially, these bounds for your bet just ensure that this is non-negative, so that your entire capital process is non-negative. Okay, so that's just a non-negativity constraint. What does the negative and positive mean? Roughly, it means that when are you going to make money in this game? If lambda t was positive and xt was larger than m, then you're going to make money. If lambda t was negative and xt was smaller than m, then you're going to make money. But if they were of opposite signs, then you're going to lose money. So roughly, the way to bet in the mth game is to say, well, if I think that the mean is larger than m, then I should bet positive. And if I think that the mean is less than m, then I should bet negative. Okay, so that's how you're going to bet, and this bet is going to depend on the data that you've seen up to previous rounds, right? So this in round t, you have seen x1 to xt minus 1. You have some idea of the distribution and the mean. You're going to use that to inform how you bet in the next round. Okay, and this is your capital process. Okay, so now all I've done is I've taken my game. I've taken my original problem of estimation and I've written down a game, and now actually I'm done. That's the end. This is my confidence sequence. Okay, the set of all games in which my capital is less than 1 over alpha. So alpha is my type 1 error. So think about alpha as being 0.05. 1 over alpha is 20, and so I start off with $1 in every game. The games in which my wealth is less than 20, that is the definition of my confidence set. The games in which I did not make enough wealth yet. And the theorem is that for any betting strategy, no matter how you did these bets, this is actually a confidence sequence of the true mean. Okay, so we are done. All we did was translate the problem to a game, and we're done. We didn't. It's kind of crazy, but we're done. So the two questions that I'm going to answer in the next few slides are why? Why is this a confidence sequence? Why is it a valid confidence set? And then, so the claim is that for any betting strategy, it's a valid confidence set. So why is that true? And the second one is, well, how should I bet so that it's a tight confidence set? Okay, so we're going to talk about validity and efficiency separately. First question is, it's always valid. Why is that? And then what is a good betting strategy so that it's actually efficient or small? Okay, so we'll handle those separately. But if there are any questions, this would be a good point to stop. So all I did was take the original problem, write down a game, and then I'm already done and I have a confidence sequence. So it seems extremely straightforward to derive a confidence sequence. Yeah.
Can you repeat again what this equation is saying? Is it like the hypothesis that m is the mean?
Yeah, I'm going to. That's on the next slide, but yeah, that's in the proof. but hopefully the procedure is at least simple. I play many games in parallel. I start each of those games with $1. I bet separately in each of these games, and then the games in which I have not made enough wealth, that's my confidence set. Okay, so that's very simple. Okay, so now first, why is it a valid confidence set? Okay, let's start with that. Oh well, sorry, first the fact that this works well. Okay, yeah, I have figures to show you it works well. So of course this is a non-parametric estimation problem. There's no reference measure for this problem. So if I take bounded random variables on the range 0 to 1, it includes discrete and continuous distributions with any support, and so there is no common reference measure. You can't use the Lebesgue measure, you can't use, so you don't have likelihood ratios, anything of that kind. But of course, when I run a simulation, I have to draw the data from some distribution. So in this case, I'm drawing the data from some beta 1030, but the procedure doesn't know this, right? So it's a non-parametric estimation procedure. So this is the PDF of the data. On the first plot, I'm going to show confidence sequences. Second plot, confidence intervals. So there's some small difference between them, and the x-axis in both of all these plots is the sample size or the time, and in the first plot, the y-axis is the actual raw confidence sequence. So the data, the mean is 0.25. So that's the dotted line. That's the quantity I am trying to estimate or cover. And these things that you're seeing over here are the actual confidence sequence produced. Okay, so anything to notice, first you can see asymmetric. It's an asymmetric confidence sequence. Secondly, like if you look at, maybe let's look at the confidence interval for simplicity. If you look at the confidence interval, I'm comparing it to, let's say, the Hofting confidence interval I presented to you and the empirical Bernstein confidence interval I'm close to. There's no much tighter both of them. And if you look at the width, this is instead of looking at the raw interval, if I just look at how wide it is, from an extremely small sample size, single digit sample size, till thousands of samples, it is much, much tighter than Hofting or empirical Bernstein. Now these are only two comparison points, but in the paper we have many, many more. So this is a very well studied problem, and there's papers by Anderson, by Bentkus, there's just a lot of answers to this question, and we compare against all of them. There will be just too many lines on the plot to show you, but yeah, betting is always significantly tighter than all of those. Yeah, this this is literally the set that we have constructed. Yeah. Sorry.
Several questions.
Yeah, sure.
So when you say confidence interval, for your algorithm, it's just same as the confidence sequence?
No. The way we bet is slightly different for a confidence interval and confidence sequence. It's just for the betting strategy that it's still constructed using the same thing, but the way you bet, if you know that I only want something tight at time n, as a fixed time n, I want it to be tight, then you can bet slightly differently. If you want something that really is tight uniformly over time, you bet slightly differently. But yeah, but they're still based on the same idea with slightly different ways of setting the betting strategy. Yeah.
So the betting strategy that you do in both these plots is optimal for the corresponding setting?
Yeah, it's just fixed n versus uniform over n. So in this case, it's a confidence sequence. You have no idea when you're going to stop, so you just want to be kind of tight over all times.
And is in that setting,
yeah, that's right. Yeah, basically, it's essentially optimal. Yes. Yeah.
So I have one more question. This is a weird question. So I want to compare this with Chernoff. I know Chernoff you can't use for estimation.
This is Chernoff. Yeah, this is Hofting bound is a Chernoff bound.
What I mean by Chernoff is that the right large deviation exponent, the I of theta. Hofting is a very loose.
Yeah, but you have a non-asymptotic confidence interval that I can compare it to. I'm happy to do it. So give me a non-asymptotic. Yeah, this is so okay. So the way to think about this, and I can say it right now, is that it is a tighter Chernoff bound. That's going to be the theme of the entire second half of the talk. But essentially, you should, when you see this, it looks weird, but you say that's actually a tighter Chernoff bound than what we really use for Chernoff bound. So why is that? When you squint at this, I'm going to use this simple inequality, but you know that log of 1 plus x is kind of approximately x minus x squared by 2. So 1 plus lambda x, which is what I'm using over there, is approximately exponential of lambda x minus lambda squared by 2 times x squared. Okay, so when I'm looking at the product of these guys, you should squint at it and say, well, I'm really looking at a process of this kind, and this is exactly what is under the hood of Chernoff bounds, is an exponential super martingale of this type, except that over here I get something that's data dependent. It's a variance dependent term, but if you use anything like a sub-Gaussian, we'll get to this later on, but you cannot put in an x dependent factor. Usually this is a constant over here, and the place that Chernoff bounds lose is essentially the fact that they cannot use something data dependent over here, and the fact that this is usually a super martingale, and so a super martingale corresponds to in a game you throw away money, while this is actually going to be exactly a martingale, which means you don't throw away money. So essentially there's a very tight connection. In fact, in the paper we have an entire section dedicated to what's the connection to Chernoff bounds and why are we beating Chernoff bounds, why? And the intuition is this is a Chernoff bound in disguise, but it quashes the looseness in Chernoff bounds. Chernoff bounds have an inequality in them, and you'll see in the proof that we don't have an inequality. So, okay, so let's actually get.
A follow-up question.
Yeah, sure.
Comment on so typically in statistics, when we come out some confidence bound, so it's easy to write down the functions of x and or the mean and sample mean and sample variance. So, what's the computation burden for this one?
That's a good question. So let me get to this. Yeah, this is a good question. This is not so hard to compute. So essentially, turns out that for certain betting strategies, you don't actually have to compute for every m. You can only maintain the outer edges of the boundary. So you really only have to look at the endpoints of the boundary and only maintain those. But even if you did something naive like just grid up 0, 1 and play this game separately for each m, this is like a very simple computation relative to let's say training a deep net or something. This is really like a linear time computation for each m. So yeah, it's actually not that hard to compute, but I can write down a closed form expression also for this. This is not closed form, but I'll write down later on a closed form expression. Yeah, I'll actually.
Inequality, but inequality for Bernoulli.
That's right. Yeah. So for exact Bernoullis, this is equivalent to inverting the sequential probability ratio test. That's exactly for Bernoullis. It matches that, but when you move away from Bernoullis, we don't know how to do that. You should think about this as being the right sequential probability ratio test for any bounded random variable. But that idea is weird because because where's the likelihood? I don't have likelihoods for this class of problems, but this is a non-negative martingale. It's playing the role of a likelihood ratio. So that's what's going on under the hood.
Yeah, but we could also have thought of it as 1 by t upon 1 by t, like the.
Okay, an empirical this thing, but that's not a non-negative martingale. So the empirical likelihood ratio thing doesn't have a martingale property, but this, as we'll see in the proof, it does. So the key part of the proof is this martingale property. So anyway, so here's the proof on one page of validity. So why is this actually a correct confidence sequence? So what you should think is happening, that's why yesterday's talk was about testing, because confidence, like estimation, is really a reduction to testing. And so what we're doing is implicitly for each m, we are testing the null hypothesis that the mean actually equals m. Okay, and this is our capital process for testing that particular hypothesis. And then I claimed that if I just take those capitals that are less than 1 over alpha, that gives me a confidence sequence. And here's the proof. It's just this is just intuition, and this is the claim. But the proof is really one step. You forget about all the games that you're playing, and you focus your attention on one game, the game that is indexed by mu. Okay, that's a very special game. You don't know which game that is, but there is one special game, the one that's indexed by the true mean mu. And I claim that when I plug in the true mean mu, this capital process is a non-negative martingale with initial value 1. Okay, it's non-negative because my bets were constrained to leave it non-negative. It has initial value 1 because I started with $1 in every game. So the only thing that you need to convince yourself is that this is actually a martingale when I plug in mu. Okay, and that is, again, I think we saw this yesterday, but otherwise it's super easy to see. So the expected value under P of, so we have this of kt superscript mu given the past, and this is for any p with mean mu, right? So this is for any p with mean mu. If I look at this, then I get kt minus 1 comes out because that's only a function of the past, and I get the expected value under p of 1 plus lambda t mu times xt minus mu. Okay, and I'm given the past. Okay, so I get given the past, and the idea is that somehow this is predictable, so it's a function of the past. So when I take this expectation, this is mean 0 because xt has mean mu, and so I just get 1. So this is just equal to kt minus 1. So it's kind of obvious, like if you just stare at it, it's kind of obvious the thing you're multiplying by has mean 1. If I plug in mu, the multiplier, the last multiplier has mean 1. And it is mean 1 because it's 1 plus xt minus mu. So xt is mean mu, so it's mean 1. So it's clearly a martingale. It's very simple to see that. And then yesterday we saw this fundamental inequality, which was Wheel's inequality, which says that the probability that my capital process ever exceeds 1 over alpha is at most alpha. Okay, that particular capital process. And essentially my confidence set is incorrect. I make a mistake only if I kick out mu. Okay, that's the only way I can kick out. But that means that what does it mean to kick out mu? It means k mu t exceeds 1 over alpha. But this theorem says that the probability of that happening is at most alpha. Okay, so with high probability, I don't kick out mu because that particular capital process will never exceed 1 over alpha. Because for that particular game, I'm playing a fair game, and my capital process starts off at 1. It's a non-negative martingale. It kind of fluctuates, and it doesn't exceed 1 over alpha. So k mu t is going to look like this over time. This is k mu t. It starts off at 1, and it's just going to kind of fluctuate. But with high probability, it will never cross 20. So that's what Wheel's inequality is telling you. The probability that this entire process ever crosses 20 is at most 1 over alpha. Is at most alpha. So that's the proof of correctness. Essentially, correctness just says I'm not going to kick out mu with high probability. Any questions about that? It's super straightforward and transparent to see why it works. So then the next question I have to answer is, how should I bet so that it's actually tight? Okay, it's valid, but how should I bet so it's tight? So this is the first. So we have many betting strategies in the paper. There's only 2 that I think are worth actually presenting to an audience in terms of simplicity to describe this. They're all simple, but this is easy to describe. So I call this one GRAPPA, which is it's called growth rate adaptive to the particular alternative. Okay, so you forget about the full form, but essentially this is what an oracle would do. So if I was an oracle that knew the distribution, what I would do is that for any game in which m is not mu, I want my wealth to grow exponentially fast. And we saw this yesterday, that I'm playing these betting games. When the null is false, my wealth can be made to grow exponentially fast. And I want to maximize the rate of growth of that exponent, so that's why I'm looking at the log wealth. Okay, so I look at the log of this multiplier. So at the tth step, I want this multiplier to be as large as possible in the log sense. And we discussed yesterday a lot why log comes up, but I'm going to look at the expected log given the past. Okay, if it's an IID problem, then you can forget about this past. And after this expected value under p, and I'm trying to find the maximum lambda. You can think of lambda as being in that range -1 by 1 minus m, whatever, but just -1 to 1 is just for simplicity. So if I was an oracle, this is actually what I would do in round t. This is how I would bet. But the key part I don't know how to handle is I don't know p. I don't have the distribution p, so how can I mimic the oracle? So answer is very simple. When this is an optimization problem, just blindly differentiate and set it equal to 0. Okay, just do that. Just differentiate and set it equal to 0. If you do that, okay, maybe I'll do it here because it's actually simple enough to do it. So you'll get this equation that looks like 1 plus lambda star times xt minus m times xt minus m is equal to 0. Okay, so you'll I have to have this expected value first. So this expected value under p. So let's just say I can pass the differentiation through the expectation, and then I differentiate. When I differentiate with respect to lambda, the log term, I get 1 plus lambda thing, and then of course I have to take that. So that's xt minus m. So I get this kind of a term. So that's what lambda star should satisfy. Okay, now it's weird because lambda star is the denominator and this expectation is over both xt's. So whenever you see anything like this, is what I do. I just do a Taylor expansion. So 1 plus this I write as expected value under p of xt minus m times 1 minus lambda star times xt minus m, and I say this is equal to 0. So this is an approximation, and I say, well, let lambda star satisfy this. But this is very clean because now it depends linearly on xt and quadratically on xt. So now it's just a quadratic equation in lambda. So I mean, not in, it's a linear in lambda, but if you look at lambda star, then this equals the expected value under p divided by x the whole squared. Okay, so that's what you get for the optimal lambda star if you do that. And now the problem still remains that I don't know p, but I have data from p, so just plug in. Okay, so essentially what you do is you just differentiate, set it equal to 0, do a Taylor expansion, and now the last step you just plug in. You have the first t minus 1 data points that you have seen from p, so just plug that in, and what you get is this sort of an expression. So when you have the expected value of xt, you just get the sample mean of xt, and when you have this kind of a variance term, you get a sample variance term. Okay, that's what it is. But this is actually a very sensible bet. So if you just look at this bet for a moment, what we have derived, maybe we had an approximation, but remember that any betting strategy is valid. So I don't have a problem that this is a valid betting strategy, I can use it. I'm not going to violate it being a confidence sequence. But this is a very sensible betting strategy. It's saying when I'm playing game M, if my sample mean so far is larger than m, then I should bet positive. And if my sample mean so far is less than m, then I should bet negative. That seems like a reasonable thing to do. And the denominator is saying, well, if my variance is small, I can bet aggressively. And if my variance is large, I should bet more conservatively. So it's very intuitive in terms of the direction, the sign of betting, as well as the magnitude of betting. It's a very intuitive bet. This is a general form of a Kelly bet. A Kelly bet, if you look at, like, it's typically going to look like a mean over variance kind of bet, and it's a very sensible bet. Okay, so I can actually use this to bet, and this is actually what's in the plot. So in the plots that I have, this is the Grappa strategy. It works super well out of the box. So this is a plug-in way. Another way of betting, so second option is actually a mixture. So instead of doing this, plugging in a particular quantity, what you could do instead is say, well, there's this is the wealth process. If I pick a particular lambda, I don't know what lambda is the right one, so let me just mix over lambda. Just choose a distribution, let's say like uniform, and I'm just going to mix over lambda, and I get a slightly different expression for the confidence set. But remember, a mixture of non-negative martingales is a non-negative martingale, so I don't violate validity. But essentially what this mixture method is doing is saying that as long as I have some mass around the right lambda, that's going to grow exponentially, and so this entire mixture is also going to grow exponentially fast. And so we can use the connection to Cover's portfolio optimization to analyze its performance, and just an uniform mixture will do. And in practice, you say, well, how do I actually do this in practice? You can just discretize the mixture. There's nothing in this that needs it to be a continuous mixture. You can have a discrete mixture instead. So I would just discretize it at some 20 points or 30 points and run it, and it works well. So like so there are kind of only two ideas. Remember, to deal with composite alternatives, there's only two ideas. One is plug-in, and that's what the Grappa method is. The other one is mixture, which is what this method is. So, and both of these you can kind of amend them to make it practical. Okay, so here's an example for what those bets, like just to really visualize how you're betting in the different games. So these are two different problems. So this is, let's say the data is coming from Bernoulli half versus the data is coming from beta 1 1. Okay, and this is, I'm plotting the lambda values for different games across time. So in this case, like this green line in the middle is when the m is 0.5. So here the true mean is actually 0.5. So what's happening over here is basically saying there's no point betting. So the bet lambda just converges to 0 and says, in this particular game, when I'm betting against the true mean, it quickly learns that there's no point betting, that it's a non-negative martingale, I'm not going to make money, so it just stops betting. Okay. If I'm looking at m being 0.45, which means the true mean is larger than m, I get a positive bet. And if I'm betting against 0.55, which means the true mean is smaller than m, it converges to a negative bet. And if I'm betting against something further away, so if I'm looking, is the mean 0.7? There's a lot of evidence that the mean is not 0.7 because the mean is actually 0.5. So I can bet more aggressively, and so it does that. So the absolute values of the bets, as you are betting against nulls that are further away from the truth, you bet more aggressively automatically. So that's very natural. And if you look at beta 1 1, it has the same mean of 0.5, but it has a lower variance than Bernoulli half. So you get the same kind of plot, but just scaled up. So this is saying from the very start, I can just be more aggressive. And the dotted line is the optimal bet. So like in this case, we can actually just calculate what's the optimal bet. Since I know this distribution, what's the right way for me to bet? And you can see that these empirical Kelly-like bets, they they're like quickly converging to the right bet. I mean, they fluctuate a little bit, but they quickly converge to the right bet, and so this wealth will grow exponentially fast at the right rate. So, and this is kind of visualizing that. Yeah.
Can you comment what happens, say for example, in the real world application, you want to predict the rate of rare disease, right? And then in that case, you true mu in your plot, the xt minus from the Bernoulli distribution with the p very small, 0.001.
Yeah.
So in that case, can you comment on what's the behavior?
Okay, I haven't looked at that, like at such a small p yet. I think it would be interesting, but I don't see a problem. Meaning, fundamentally, that problem is very hard, and so you'll have an asymmetric confidence set, which is larger on one side and smaller on the other. But it will have the right meaning the right exponents and the right behavior, because we can prove that these tests are they are actually optimal even in the non-parametric sense for this so it's adaptive in the parametric problem. It will achieve the right parametric rates.
Yeah, because if in your plot, I feel that the initial stage is bumpy up and down.
Yeah.
It will take much longer.
It will, yeah, but that's just because the problem is so hard. So that's true for any method. So in the Bernoulli case, this this is a non-negative martingale, and in the Bernoulli case, the only non-negative martingale is the likelihood ratio. So essentially, this is a generalization of the SPRT to the bounded distributions. And if you're in the Bernoulli case, it's exactly the SPRT. In that special case of Bernoulli, you're doing nothing. So we know that the SPRT is optimal for that problem, and so you're going to get the right behavior out of this martingale as well, because it's really an SPRT in disguise.
Slightly different for the confident interval is SPRT, because Bernoulli distribution for the confident interval you cannot get exact 95.
Yeah, exactly. So you won't get exact. It's a conservative confidence interval, right. But the only inequality in the entire. So if you look at this proof, there's only one inequality in the whole proof, and that's this inequality. And it's like the question is, when is this equality tight? Everything else is this is the proof, and so this you can ask yourself: how close is this to being equal to alpha? And the answer is subtle, I guess. It's related to overshoot and stuff of that kind. But usually it's quite close to being alpha, because we know that for continuous path non-negative martingales, Wheel's inequality holds with equality, and the only problem that's coming due to discretization, and so this holds close to equality. But I agree, it's not exactly 1 minus alpha. It will be conservative. That's right. So I guess an interesting question is, can you get another non-asymptotic confidence sequence that has an overshoot correction? But as far as I know, once you get into overshoot stuff, it's going to not be non-asymptotically valid. So, okay. I guess here are some more plots. Yeah.
Quick question
on
what you just said.
Yeah.
So you said will is tight in some setting.
The will is tight if I had a continuous time non-negative martingale, which is basically geometric Brownian motion. Okay, so if I have geometric Brownian motion, Wheels holds with equality. So for what is geometric Brownian motion? It's exponential of lambda times bt minus lambda square by 2 times sigma square t. So that's geometric Brownian motion with variance sigma and centered. And so for this particular process, this is a non-negative martingale in continuous time. It's a continuous time, continuous path non-negative martingale with infinite quadratic variation. And so for this kind of process, the Wheel's inequality holds with equality. Okay, and so essentially, when you go from continuous time to discrete time, the only thing that really changes, we still have non-negative martingales with, if we keep betting, it has an infinite quadratic variation. The only thing that changes is it's not continuous path. The path jumps, and so it holds like approximately with equality. The only thing is there's some overshoot, that is you cross the boundary of 1 minus alpha discretely. So this causes some slight looseness, but it's not a lot. So you get 0.49 or something like that. You'll get very close to 0.05.
Markov is never tight, right? So
Markov is not tight at all. It's very far from tight. But this is time uniform Markov. It's really saying the same thing, but now it's talking about the whole path. Markov is saying at any instant. That's super loose. But I have now a union bound over all time that's helping me actually take away the looseness of Markov. Yeah, thanks. Sure. Okay. Here's just a couple more things to compare with. I said there's a Bentkus confidence interval, there's an Anderson confidence interval. So we have some more comparisons, but over here you can see like the betting one, the green dotted line is just visually like just the width is much tighter than all of these other analytic methods that people have developed in practice, and this is just for another example. So across examples, beta 11, beta 1030, it's just much tighter. So what can we actually prove? So we can prove, for example, that this is, it's an interesting statement, but something called Bernstein's inequality, which says, suppose I gave you the true variance, well, I can form a Chernoff style confidence interval using Bernstein's inequality instead of Hoeffding's inequality, and we can show that this scales as 1 over root n, so you have to scale by root n, but we can show that our confidence set is basically going to be tighter than Bernstein in the limit. Okay, so it's and so essentially we match or beat the leading term of Bernstein's inequality, even though we don't know sigma. We don't have the information of this variance. So you should think about this as being a tight empirical Bernstein essentially. We can say something more. The right width behavior should actually be related to something called KL-inf. And we get that KL-inf term, but this is maybe more easy to state to give you some intuition of what's going on.
Question.
Yeah.
Is this for the interval case or the sequence case?
For the interval. Yeah. For the interval, it's tighter than
Bernstein confidence interval.
Exactly. Yeah, that's right. There is. I'll get to that in the next half of my talk. There is a sequential Bernstein. Yeah. Okay, and so we see some more plots. So this is Bernoulli case. So here it's Bernoulli 0.1. I don't have something so small like 0.001, but so this is Bernoulli 0.1. That's the true data, and you see this asymmetric confidence sequence. But now you see the methods are kind of getting closer to each other because somehow, actually in the Bernoulli half case, we still have an improvement, but the methods are getting closer because somehow Bernoullis are the ones that extremize the variance, and so this variance adaptivity doesn't help as much. So, but it's still better. I mean, you still get an improvement over all of these other non-parametric methods. Remember, these methods are not tuned to Bernoullis. They have to be valid for any bounded distributions. What you'd like is, it's still good for Bernoullis, and yeah, it is still good for Bernoullis, even 0.1 or 0.5. So pretty good. Okay, so I want to make an interesting point that
This is because you may be moving here.
Yeah.
So one of the big things here, it's true in all your plots as well, is the non-asymptotic.
Yes. Yeah.
Not just validity, but the non-asymptotic width.
Yeah.
But then the theorem you showed us was an asymptotic statement.
Yeah, just so that it's clean.
Okay.
Yeah.
Do you have some version of a non-asymptotic statement?
Yeah, that's that involves the KL-inf and stuff like that. It's a little ugly. Yeah, not so easy to present quickly.
But it is like the spiritual message is that it's optimal. What is the way to think?
Very tough for confidence intervals. Optimality theory is very weak. Like this is, as I was saying yesterday, it's nothing to do with our problem. But in general, if you take up, for testing statistical hypotheses, we have tons of impossibility, possibility results, lower and upper bound matching, things like that. For confidence interval widths and sizes, we just don't have optimality theory as much. It's just very, very badly developed, even for parametric problems. We just don't understand optimal widths of confidence intervals, even for very simple parametric problems, maybe yes, but no general theory that you can look to. And even in the univariate case, but when you get to multivariate case, forget it. Like, I mean, I don't even know, should you look at the Lebesgue measure of the set? Should you look at the diameter of the set? Should you look at what's the right metric for measuring optimality? And then where are the results showing that, so it's very weird. I've discussed this a lot with Larry and Siva and others like that, because we have this paper on universal inference and we're trying to compare. There's just hardly anything on optimality of confidence sets, and that's sad, but
even if you have like Oracle baselines, there isn't a way to think about it?
Yeah, we just don't know what the optimal width of the confidence set is for bounded randomly. We just don't know what the right answer is. What is the optimal width? So like somehow for the test, we know the right answer. So for the test, we know the optimal growth rate of the wealth, and we know the optimal stopping time. It should look like log 1 over alpha by KL, some kind of a KL divergence. You have to be careful with KL because there's no reference measure here, but it's a KL-inf that I presented yesterday. So that's like the right form for the stopping time, and for the growth rate it's the KL-inf. So we understand the testing very well. As soon as you go now, it's a family of tests. So all a confidence set is it's inverting a family of tests. But these tests have to cooperate with each other. They have to cooperate to get small width. You can't have, if some tests reject in some situations while others don't, then that's not good. So somehow all the tests have to be aligned. You have to align all the tests well so to have small width, and we don't understand in an optimal sense what's the optimal way to run pointwise tests. So somehow you can't just, it's not easy to piggyback on optimality of tests to give you like optimality of confidence sets directly, because again even the notion of optimality is not clear. What should you be measuring? How should you measure optimality? Maybe for intervals it's clear it's width, but as soon as even 2-dimension, you're like, should you take diameter or Lebesgue measure? Like what? Yeah, volume.
Okay, so sorry, one more follow-up question.
Yeah.
So here I could have picked the oracle. So forget asymptotia for the moment, but I could have picked the oracle to be the true population CDF of
Oh yeah.
the underlying distribution.
Population CDF.
Or whatever. Not
No, this you know the CDF.
Yeah.
How do you get a?
Like if essentially, is there a way to? Or it's a question, it's not
Yeah.
a statement. Is there a way to, instead of making the oracle the Bernstein oracle,
Yeah.
which is literally all families of
Yeah, yeah,
distributions
yeah.
that have that
Yeah.
variance and satisfy a Bernstein
Yeah.
inequality, I have an underlying distribution.
Yeah.
So can I change that oracle to match the optimal width for that distribution, and would you compete?
Don't know, but I don't even know what the optimal would be if I just gave you some distribution. What the optimal width confidence interval would be for some particular distribution. I mean, presumably it would be an inversion of a likelihood ratio test. But when your test, so it corresponds to you test each theta against not theta. So and you invert these tests. When you're doing not theta, so like the alternative. You're testing is the null equal, I mean the null is it's theta, the alternative is it's not theta. So when you ask, when you have to mix over the alternatives, what's the right mixture to use over the alternatives? So what's the right, it's very easy to come up with a test that's testing is it theta if you know the distribution. You take a likelihood ratio where the denominator is p of, p with mean theta, and then the numerator is that's the problem. The problem is the alternative when you're saying it's not theta. And you have all of these tests, you're testing at every theta, you're doing a test, and each test is looking at what if it's not theta. So for all of those tests you have to pick what to do for the alternative in a way that they're aligned. So it's not clear.
Fix the parametric fact
Yeah.
I'm dealing with. It's the fact that I'm mixing over alternatives that's the issue. The fact that the null simplifies.
Yeah, exactly. Yeah, that's right. Yeah.
Maybe I can add our comment. So you like the non-asymptotic, even for the Bernoulli distributions. So given in the sequential analysis, also called the fixed width confidence interval.
Yeah.
So you want to what's the sample size you needed for the confidence interval, say 0.001. That's an open problem. What is exact non-asymptotic is that open? Even for the
Yeah. We should think about it. I think it's too basic a question to be open. Like I feel like, yeah, correct.
To build up on Ash's first question, so you said that you have, so at the beginning you showed Hoeffding, you showed Bernstein, you showed a formula. So what you're saying is you have a similar formula in your case, even though it's ugly and it involves.
No. I have. There's another version which I can write down, which is closed form, which is a little slightly tedious to write down, but I can write it down. It turns out that okay, so let me just write it down. So here's a better empirical Bernstein bound. That meaning it's better than it's in between the betting bound and all other bounds in literature. So it's slightly looser than betting, but it's closed form and better than every other existing closed form. Okay, so here's what it looks like. It's tedious, but it's going to be okay. Be more careful. So it looks like the sum of. So now lambda I is not going to depend on m. There's only just going to be one sequence of lambda i's, 1 to t, divided by the sum of lambda I is equal to 1 to t. So it's centered at not the sample mean, but a weighted sample mean. Sorry, be patient. Sum of I is equal to 1 to t I times xi minus mu hat I the whole squared. Hat I minus 1 the whole squared. Okay. Okay, so it has this form. Okay, so I'm using this formula psi e of lambda I. This is going to come up later in the talk, but psi e of lambda I is minus. So psi e of lambda is minus log of 1 minus lambda minus lambda. Okay, which if you do a Taylor expansion looks like lambda squared by 2. Okay, so psi e of lambda is, we call it the sub-exponential psi function. It's actually related to the CGF of an exponential distribution and things of that kind. It's like the log CGF or something of that kind. But it's like when you look at it, you should look at it and think, okay, it's roughly lambda squared by 2. Okay, so I have this term over here, and this is actually an empirical variance type of term. So it looks like xi minus mu hat I minus 1 is, this is mu hat I. So I'm calling this mu hat I. Okay, and this is like a running empirical variance that I have so far. Okay, and so it looks a bit funny. Okay, but it turns out that that if you set lambda I appropriately, and what I mean by appropriately is you should set lambda I like square root of log 1 over alpha by sigma hat squared times t log t. Okay, so there's a particular way to set lambda I. Where does this, why set lambda I this way? If you look at this formula, it should remind you of gradient descent. When you look at the convergence state of gradient descent, look at the step size, you have a sum of step sizes and a sum of step sizes squared. And the typical thing is, well, you want the sum of step sizes to go to infinity and the sum of step sizes squared to be small or finite, or something of that kind. So you want to set this to be like 1 over square root t, so that the sum of squares is like 1 over, it's like 1 over t, which sums to like log t or something like that. When you do it this way, it really sums to log t instead of log t, but it's like a minor point. So that's why it looks like 1 over square root t. You should have a square root log 1 over alpha dependence on the overall width. So that's why this is square root log 1 alpha. Anyway, but this is actually a closed form betting fraction. So this is how I'm just going to set lambda I. These are my bets, and this is the width that I get. This is closed form. So I have a centered at some weighted sample mean, and this has some width, and I can prove that this width is the same bound, which is root n times the width of Cn minus root n times the width of Bernstein is actually less than or equal to 0. Okay, actually it's in the limit. So this is exactly an empirical Bernstein inequality that matches Bernstein in the limit. It's closed form and it matches Bernstein in the limit, and no other empirical Bernstein inequality in the literature has that property, including Maurer and Pontil. If you look at Maurer and Pontil and you look at root n times their width, they don't match Bernstein in the limit. And you look at there's many other empirical Bernstein inequalities in the literature, they're all loose, and the reason they're all loose is because they don't have the right proof technique. The right proof technique over here involves, instead of using this particular martingale, it uses a particular very interesting super martingale, which is you do the same proof, but the super martingale is actually lambda I times xi minus mu minus psi e of lambda I times xi minus mu hat I minus 1 the whole squared. So it turns out that the process that looks like this, I is equal to 1 to t. So instead of using our wealth process, which look like the product of 1 plus lambda times things, remember I told you, it looks approximately like this form, but this is only an approximation. This is exactly a non-negative super martingale. This is a non-negative super martingale for any bounded random variable. That this depends on the variance, the actual empirical variance of the data. And if you use this and apply Wheel's inequality, you get this closed form. So essentially, instead of using our not closed form bets of this type, you just say, I'm going to use a different one, and I'm going to use this one. And then this leads to a closed form interval that matches Bernstein exactly in the limit. So if you really are lazy and you want something in closed form, you don't want computation, I would use this. If you're willing to do some discretization and computation, then I would use this. And the gap is very small, but it's visible. You'll see that betting is tighter. And the reason betting is tighter is roughly what's happening away from the null. So essentially these bets are going to 0. But actually, if you're away from the null, you should bet at a constant that never goes to 0. Actually, you should the optimal bet when you're betting, if the true mean is 0.5 and you're betting against 0.7, then that bet should actually never go to 0. It should just be a constant. But the thing is that bet becomes irrelevant as soon as your wealth crosses 20. That becomes irrelevant. So somehow the bets that really matter are the things that are close to the true mean. And those bets, as you get closer and closer to the true mean, those bets are really going to 0. So somehow this is in spirit the right thing to do. And so anyway, so since several people asked about a closed form, here's a closed form that matches Bernstein in the limit.
So where is KLN? Oh, sorry, go ahead.
Yeah, KLN doesn't appear for this bound. It appears for the other one. So if you really want KLN in the right term, you have to use this one. This one, it's really a Bernstein limit. So
this is a more speculative question, but for these bounded random variables, you can go like whatever, Hufting, Bernstein, Bennett, etc., etc.
Yeah.
Each of those is associated with its own Orlich norm. So is there a way to somehow translate that Orlich norm into a super martingale?
Next half of the talk, we'll see. Yeah, at least to some extent. Yeah.
So I try to understand it. So this kind of a beta lambda t or lambda equals to 0. But in the first term, it seems like when you estimate, you still put a bit more weight.
Yeah.
The initial data. So but data is ID.
Yeah.
I think in the sequential analysis, in often cases, you want to put more weight on the later observation.
I agree. We don't have a way of doing this. So I've thought about this also. In fact, if you're familiar with the optimization literature, this was a motivation for Nesterov's dual averaging. So he said, well, when I do gradient descent, the step size goes to 0. But if you actually look at if you look at xt, if you're doing gradient descent, xt is essentially a sum of gradients. It's x0 minus a sum of gradients essentially. And he's like, sum of weighted gradients with a step size. And he said, as I'm getting closer to the optimum, the gradients should have more information, but I'm weighting them less and less. This is super weird. And he said, well, that's not nice behavior. So I'm instead going to define something called dual averaging, which actually has the opposite behavior. And I'm going to somehow weight my way. So that was his entire motivation of dual averaging. So this, what I have is, you should think of as the gradient descent analog in our space. I don't know of a dual averaging analog in our space. Like, how do you have somehow the more recent points matter more or something? I don't know how. I don't know how to do that. So I've tried, and it just doesn't seem to work with my current set of methods. So as I said, anyway, the right thing to do is really this. This is some first order approximation to that.
So that's how you set up the game with that 1 plus lambda x.
Yeah.
One can think of this as a different game, right?
It's the same game. I'm using a different capital process.
Oh, I see.
Yeah. So essentially, just how is my wealth changing? This is the multiplier of my wealth.
I see.
It's a different game.
It's a different game.
Yeah, this game structure is the same. The payoffs are different. Yeah, that's right. The payoffs are different. Exactly right.
So what I meant.
So in this game, this is actually a non-negative super martingale. So what this corresponds to is essentially the fact that under the null, you're going to throw away some money. Like here under the null, it's exactly a non-negative martingale. What that means is your expected value of your wealth at any fixed time is the same, at any stopping time finite, it's the same, things like that. This is a non-negative super martingale. It really is a super martingale. It really means that even under the null, I'm kind of going to be losing money. So that's why it's going to be slightly worse than this one. So you would never, the way you should think about it is that you're allowed to choose any betting function. This is also a valid betting function because under the null, the expected value is less than equal to 1 of the increment. This is also a valid betting function. If you were really betting, you would never choose that one compared to this one. This has expected value equal to 1 if the null was true. This has less than 1 if the null was true. So you never actually pick it, but it's available to you. This is a valid bet. And if you want to say, I want to use this bet, you can use that bet. It's fine. But that's a nice, analytically nice bet, but not really optimal if you want tight bounds.
I have a high level question. So when you set up, so you have this framework about going from statistical problems to games, right? And then the first step is to set up the game.
Yeah.
So you showed us on a slide saying this is the game.
Yeah.
But there may be multiple other ways of setting up.
But remember the more general definition of the game is under the null hypothesis you shouldn't be able to make money.
Correct.
And so it's like you can choose any betting function that doesn't. So the real I chose the betting function and wrote it for you, but you can choose any function s from yesterday such that expected value of s is less than equal to 1. Mm-hmm. And so different betting functions, different nulls correspond to different available bets out of which you have to pick one. And that's why yesterday we said, well, what's the optimal one to pick? All of these are available to you, what's the optimal one to pick, and it was based on this reverse information projection and so on. And so that's the same story over here. So they're available to you, but why would you pick anything other than something of this kind? So you can show that these are the optimal bets are actually of this. For this game, for the bounded mean, optimal bets must look like that. That's how they look. In other words, the numeraire E variable from yesterday is actually of this form for the bounded mean betting game. It's 1 plus lambda times the optimal bet is of that form.
Cool, thanks.
Yeah. Okay, so this might seem like, oh, it's this approach via betting. It's one way of solving the problem, but actually this is the only fact that I used in the whole I only used the fact that this is a non-negative martingale, but this fact that it's a non-negative martingale, S martingale because it has initial value 1, this is actually equivalent to the problem statement. It's not an implication of the problem statement. The problem in Chernoff bounds is we start off with the problem statement and then we derive some kind of implication of it, some kind of thing is bounded by 1, some kind of MGF bound. But actually the fact that I've used is completely equivalent. Instead of telling me, Aditya, xi has conditional mean mu, each of these xi's has conditional mean mu, you could have told me, Aditya, this process is a test martingale, and you've told me exactly the same thing. Like it's logically equivalent. So the capital process being a non-negative martingale is not an implication, it's equivalent to the problem statement. And this is actually not just true for this game. Even though this was a nice game to start off with to get intuition, actually there's a lot of non-parametric problems in the literature, independence testing, two-sample testing, heavy-tailed estimation, things of that kind, for which you can translate it exactly to a particular process being a non-negative martingale, and you lose nothing in that translation, which is why these methods end up being so powerful. It's because it's not a one direction implication, it's actually both, they're equivalent. And so you can show that you somehow have to use capital processes under the hood, maybe you don't realize you're using them, because Chernoff bounds, as we'll see, are based on capital processes, but you have to use capital processes for non-parametric problems. Okay, this would be the, you can think about this from an adversarial point of view, so you can think about this as a multi-round game against an, like you don't have to fix a distribution P ahead of time and have data be generated by P. That's a very stochastic view of the world. So what you can first say is, here's the game, the adversary first picks a mu in 0, 1, and each time T, the statistician discloses bets for every M depending on the past, but then the adversary picks a particular distribution Q mu T, which could depend on the past and on the bets, which has conditional mean mu, and you just essentially draw xt from that qt and present it to the statistician. So essentially there's nothing in the game that had to have everything be fully stochastic set up in advance. In round T, an adversary can pick a different distribution with conditional mean mu and give you data from that, and all of the math still works out, and you really still get a confidence set or confidence sequence against. It's a constrained adversary because the adversary has to pick some distribution with mean mu, but other than that they can pick that distribution arbitrarily, but they still can't foil you. And this is related to this idea that the set of distributions with mean mu on a bounded set, it's actually something called a fork convex set. And fork convexity is actually a sequential analog of convexity that is at the heart of why these methods work and so on. So I won't get into fork convexity, but it's like it's really an analog of convexity that I'd be happy to talk about offline. Okay, in the paper we actually don't just solve this with replacement version, we also talk about sampling without replacement. So it's a similar problem. You have some fixed numbers in the range 0 to 1. Non-random numbers, and then you sample them without replacement, meaning you scramble the bag up and you pick a number out and you look at it, it's between 0 and 1, and you toss it aside. And then the question there is, how do I estimate, I have capital N numbers in the bin, and how do I estimate their sample mean? And again, this goes back, somehow these literatures have been very different since Hoofding. Hoofding pointed out that the same interval for the with replacement case also works in the without replacement case, he said that, but it turns out that in without replacement you should get something much better, because after capital N steps you know the true mean, so there's no uncertainty left, but this doesn't shrink to zero width. So people like Surfling and Bardenay-Maillard and so on, they've kind of developed a separate literature on the without replacement case, but it turns out that if you used betting, you can write down both closed form expressions as well as non-closed form expressions that outperform existing closed form expressions and non-closed form expressions. Right? You get something significantly tighter by just playing this game via betting. Okay, so but I'll just leave that to the paper for details. Okay, we're like kind of running behind time. Maybe we'll take a 5-minute break and come back at 11:20, and I'll tell you. I told you about one problem so far, but I won't tell you, well, actually how do we construct confidence sequences for more general non-parametric problems and so on. Okay, so let's take a 5-minute break and return. nonparametric settings. Okay, so we had kind of two papers, one in the annals and one in probability surveys, that shows how to derive what are called time uniform Chernoff bounds and more general nonparametric confidence sequences. Okay, so there's two papers. So I'll first tell you about the time uniform Chernoff paper, and then I'll tell you how to use that time uniform Chernoff paper to derive confidence sequences. So the time uniform Chernoff paper, it's actually a long paper, like I don't know, 50 or 60 pages, but it's very simple. It only has one assumption and one theorem. And as mathematicians, we're like, yeah, I like papers that have an assumption and a theorem. So what's nice about this assumption is that it is going to be satisfied by tons of other assumptions that people make in the literature. So when you have non-parametric concentration, people say, well, let's assume my data is sub-Gaussian, or it has some bounded moments like second moment, or maybe the data is symmetric, or some kind of non-parametric condition on the data. And those conditions are going to actually imply our condition. So our assumption is going to be easily satisfied in tons of many cases. And then the nice thing is our theorem is going to be stronger than many other existing famous named theorems in the literature. So if you've heard of Hoeffding, Bernstein, Bennett, Friedman, De La Peña, things of that kind, that single theorem is going to be stronger than all of those, and all of their matrix versions. So matrix Hoeffding, matrix Bernstein, matrix Friedman, all of these. So assumption 1 is weaker than all of those, meaning it's implied by all of them, and theorem 1 is stronger than all of these. So I think we're going to be paying some attention to why this assumption is interesting and what this theorem looks like. Okay, what do I mean by stronger? We have an ABCDE mnemonic in the paper saying, so A means the same bound holds under weaker assumptions. B means that there's going to be a particular boundary and we can lower that boundary, we have a tighter boundary. C means we have an extension to continuous time. D means we have an extension to matrices that was not known before. And E means we can improve the exponent for that bound. So we have 5 notions of stronger. And so then we have these, we just take all inequalities that you've ever heard of in the literature, like by Bernstein, Bennett, Hoeffding, Friedman, Pinellas, Blackwell, Van der Geer, De La Peña, blah, 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 and we tell you exactly our one theorem, how it improves all of those bounds. So some of them are improved in the exponent, some of them are improved in making matrix versions, some lower boundaries, some weaker assumptions. And so it's really only one theorem, but most of the paper is corollaries to show that, as claimed, our theorem is really stronger than all of those. We just instantiate our theorem in all of those cases to show you get something better. Okay, so here's that assumption, and it's a slightly simplified version of that assumption, but I think that's fine for our purposes. So this is the assumption. So it says, given a sum process, okay, it's going to be about random walks. This assumption is about random walks. So we have a sum of random variables. So I'm going to call that sum process Sn. And we are going to have a variance process that talks about how much this random walk can vary. And so we have this variance process Vn. Okay, these two pieces, I'm going to give examples later on. That we can find some function psi of lambda. I gave this example earlier already, but essentially it looks like exponential of lambda times Sn minus psi of lambda times Vn is an E process. Okay, it's like, or you can say it's upper bounded by a test super martingale, or if I like to use this term, that this quantity is actually an E process for any lambda in some range. So there's a lambda max here, could be infinity, but the psi of lambda, if the psi of lambda is funky, like I had it here, this log of 1 minus lambda, this is only defined on for lambda smaller than 1, because of course log can't take on negative things. So in that case lambda max is 1, but this psi of lambda is going to differ depending on the non-parametric assumption that we have, and Vn is going to differ based on the non-parametric assumption, but Vn is always like a variance and Sn is always like a sum. And so this is the key assumption, and so we call this a sub-psi super martingale or a sub-psi E process. Okay, I'm going to give lots of examples, but all of the examples are going to look of this form. Now, usually the psi of lambda is a log MGF. So as I said, usually you should squint at it and say it looks like lambda square by 2. At least as lambda goes to 0, it looks like lambda square by 2. This is a property for any log MGF. It looks like lambda square by 2 near 0. So that's what you should think of psi of lambda as being. And now I'm going to give you examples to show you that actually that assumption is really satisfied in many simple cases. Okay, so let's take the example of where, suppose you're making the assumption that your data is let's say mean 0 and they are sub-Gaussian. Okay, so the sub-Gaussian assumption is saying that when I look at the moment generating function of my xi given the past, then it looks like it's bounded by the moment generating function of a Gaussian with some parameter sigma I. So that's what it means for it to be sub-Gaussian. And in that case, this quantity that appears in my assumption looks like this. It's like the product of lambda xi minus lambda square by 2 times sigma I squared. And so the sum, I mean, I've written it as a product, but if I move the product into the exponent, the sum is just the sum of xi's, and the variance process is the sum of sigma I squareds. Okay, that's the variance process. Lambda is lambda square by 2. Okay, and so in this case, if each of the means has mean less than or equal to 0, so if the conditional means are negative and xi is sigma I, this is a non-negative supermartingale for all positive lambda. There's no restriction on lambda for all positive lambda. So that's an example of the case where that assumption is satisfied. Now here is next example, which is more interesting. Assume that this example on the previous slide you can generalize to any MGF. So the fact that it's a sub-Gaussian MGF was not important. It could have been some other MGF bound, and then you can subtract the appropriate psi of lambda over here, and you can get a super martingale. So somehow anything with a bounded MGF is contained in our assumption. The more interesting case is when you don't have a bounded MGF, but you can still satisfy our assumption. So here's an example. You have observations that are actually just bounded on one side and they're unbounded on the other side. So now I'm going to define these Sn as the sum of xi's, and Vn is now random. It actually just depends on the sum of xi squareds. And this process that I had written down over here earlier, it looks like this anyway. This is the psi e function that I've written down on the board, but it's a very simple process, and the claim is that if xi is at least minus 1, all of these are centered, so I'm giving you centered versions so I don't have a mean to subtract off, but in this case the conditional mean is non-negative. If I have some mean mu, then I have to write the sum as xi minus mu. So I've removed that mu term to just keep it simpler. So if xi is non-negative and no upper bound, no tail condition on the upper side, that's remarkable. You get something that's a non-negative supermartingale for any lambda. So when you look at this, you should say I have something that looks like an MGF bound without a distribution that has an MGF. The only assumption on the distribution is that it's at least minus 1. I mean, there's ridiculously heavy tail distributions that are at least minus 1. You don't even have to have you have to have a mean for this statement to be true, but other than that, you don't even need to have a variance or higher moments or anything. But still, you get something that looks a lot like an MGF, like a sub-Gaussian type, because this looks like lambda square by 2. So it's a self-normalized, we call it a sub-exponential supermartingale. Very powerful. Okay, so let me,
Very quick question. Are the minus 1 and 0 just arbitrary, or is there any?
Yeah. So if you move it to minus c, then the psi e function changes and has a c in there and stuff like that. Yeah. Arbitrary choices. Yeah.
Sorry, if it is heavy-tailed, why does the expectation of this exponential exist?
That's amazing, right? That's the amazing fact. Yeah, exactly. But there's tons of other examples like this which I think are also cute. And maybe I'll write down a third one. I thought I had it, but maybe I just forgot to write it down. I think this one is also very cute. So let's say xi is symmetric. Okay, so xi has the same distribution as minus xi given the past. Okay, so that's the class that I'm considering. It involves things like a Cauchy random variable which don't even have a mean. Okay, then it turns out that exponential of lambda times the sum, maybe I'll write it explicitly, the sum of xi, I is equal to 1 to n, minus lambda square by 2 times the sum of xi squareds from I is equal to 1 to n. This is a non-negative supermartingale. It's just amazing. It's like I have something that's like a sub-Gaussian supermartingale, but now instead of having like a true variance in there, I have an empirical variance in there. I have unbounded random variables with no moments, like there's no moment assumption on this class of distributions. It could be discrete, continuous, unbounded, whatever, heavy-tailed, and this is always a non-negative supermartingale with initial value 1. So at 0, this is just exponential of 0, so it's 1, and it's always a non-negative supermartingale. Very easy fact to prove, but it's by De La Peña. Actually, it actually goes back to Efron in 1969. But so this assumption is actually super easy to satisfy in many cases, and many cases where you don't have an MGF. So that's why I think of it as a very powerful assumption that we need to pay more attention to. Okay, so that's the assumption. I've written it as this. So this is upper bounded by a supermartingale. So it may not be a supermartingale itself, but it may be an E process, which means it's actually upper bounded by. So it's a minor detail. You can just think about it as that's a supermartingale. And then some notation for the theorem. So that's our assumption. We have a supermartingale, and our theorem is going to involve two terms. which are functions of this psi. Okay, so psi star is the usual Legendre-Fenchel transform, and then this S of u is a very interesting thing I've never seen in the literature before. It's called the slope transform. I'll tell you why we name it that way later on, but it's some function of psi and psi star prime and things of that kind. Okay, so if you want examples, then psi star of u in the Gaussian case is still u squared by 2, and this slope transform is actually u by 2. Okay, it turns out that if you plug it all in, then you get something that's u by 2, and it's always, this is always between 0 and u. So S of u is always between 0 and u. It's non-negative. It's like, and it's u by 2 in the Gaussian case. So that's for intuition. That's what the slope transform is. So here's the theorem. So suppose Sn, Vn, and psi of lambda satisfy that assumption that it's a super martingale, and we just have, it's quite weak, but we need psi to be strictly convex and twice continuously differentiable. These are true for any MGF. So any log MGF has this property, and all of the ones that I've presented so far and we analyze in the paper, they satisfy this property. So psi of, so like lambda square by 2, psi of 0 is 0, psi prime of 0 is 0, and it grows to infinity. So some very really minor ones. So then the statement of the theorem is that for any x and m, okay, and I'll tell you what those mean, but they're essentially, you should think of them as like we're describing a line, and this is the intercept and the slope of the line. And the probability that there exists any n such that my random walk Sn ever crosses a line in Vn is exponentially small. Okay, expected value of L0 is 1. Okay, so forget this term, it's just 1. In the matrix case, it's a d. So it's a, but if you think of the scalar case, that's just 1. And this exponent should, I don't know, should remind you of Chernoff bounds if you have seen them. It's the Fenchel conjugate appearing in exponent. But now I have this statement in terms of a line. Okay, so we need to understand this a little bit more. So let's look at some more examples. Okay, so suppose xn is bounded by b and has mean 0, and let Vn be actually the sum of the variances. So there's this famous inequality, Bennett's inequality, which says this. It says the probability that Sm is at least x, m is the sample size, some fixed sample size, is exponentially small, and in this exponent you have some funky looking term. Okay, and then Friedman actually improved Bennett's inequality to say, well, this is only for a fixed m, but he said the probability that there exists any n for which Sn is at least x and Vn is at most m is the same exponent, it's exponentially small. And these are actually special cases of our theorem which say something else, the probability that Sn ever crosses a line is exponential. So this right hand side is exactly the same for all of us, but our claim is going to be tighter. I'll show you a visualization of that soon. Maybe I'll just jump to that visualization first. So this is what you should think of as what's going on. The x-axis is time or sample size, or actually it's actually intrinsic variance. You should think of this as being Vn, but for simplicity just assume that I have an IID case and Vn is just n. And this is the bound on Sn. So Sn is a random walk. My Sn starts from 0 and it's a random walk that fluctuates. And what this theorem 1 is telling you is that the probability that my random walk will ever cross this line is exponentially small. That's what my theorem 1 says. The probability that Sn, my random walk, ever crosses this line in Vn, in this case Vn is n. So this is the line. It actually passes through the point x comma m. So that's actually, it's not intercept and slope, but it's really, there's a point x comma m that it passes through. And that's our claim. And Friedman's inequality basically is this. It basically says the probability that the random walk ever crosses this line is exponentially small. And we use Friedman before and after time m. So essentially we are saying, well, it won't cross this line, and Friedman says nothing after time m, and we say, well, it's this line. So this line is kind of uniformly better than Friedman, but they both recover what's called a Chernoff bound. When you see Chernoff bounds, that's their claim is at a particular time m, and so the right hand side alpha is it's the same right hand side. So this is a time uniform Chernoff bound. So every actually turns out every Chernoff bound in literature. I'll give you some more examples. So we had the bounded case earlier. Let's look at some matrix version of this. Suppose you have a bounded maximum eigenvalue, and this Vn is a eigenvalue, maximum eigenvalue of the sum of the variance, the covariance operator. Then this type of a bound is what we get out of our theorem, but this actually strengthens Trope's matrix Friedman or matrix Bernstein inequality in the same way that I just showed you that we strengthen Friedman or Bernstein things like that. So it's for free. You don't lose anything. The exponent is exactly the same. You don't lose constants. Nothing. This is every Chernoff bound is strengthened to a time uniform Chernoff bound. You can get matrix sub-Gaussian versions of this, and this is what a matrix sub-Gaussian bound looks like. And then this strengthens the matrix Hoofding in Trope or Wainwright or Elsewhere-Winter and so on. So I think the general story is this, that behind every Chernoff bound is a time uniform Chernoff bound for free that's actually based on non-negative super martingales.
One question.
Yeah.
So in the matrix case, you have to, is your proof like super unified, or in the matrix?
Super unified, yeah, exactly. There's
Prop has to do all this leave.
no, in special, to verify that we have a super martingale, we have to use leave.
Okay.
Like that, to verify the assumption is satisfied, we use leave too. But we can now verify that thing is true in many other cases that were not known before actually. So it is a unified and shorter proof in many cases because we use certain operator monotone properties and stuff like that. So now we get certain heavy-tailed versions and symmetric versions, like for symmetric matrices and things like that, that were not known before, but now you get these kind of Chernoff, matrix Chernoff bounds for free, like in all of these like multivariate cases and so on. And then some interesting geometric fact is that this line that we have in the theorem 1, which is a time uniform bound, if I write down the pointwise Chernoff bound, then our theorem 1 is actually a tangent to the pointwise Chernoff bound curve. So maybe I won't stress on it too much for reasons of time, but it's just an interesting fact. Somehow the line is not the right answer because like if you think of this as being the variance, a sum should not scale like the variance. It should actually scale like square root of the variance. So this theorem 1 is interesting in the sense that it generalizes and improves all Chernoff bounds, but it's not the right answer if you really want to understand the time uniform behavior of a process. It should look like a curve. But once you have the optimal line, this is the optimal line, it's not improvable. But once you have the optimal, and the proof actually I should say of the theorem is simple. You apply Wheel's inequality and you optimize lambda. So like in any Chernoff bound, like you apply Markov's inequality in a Chernoff bound and you tune lambda. Here we apply Wheel's inequality and tune lambda. So it's like the proof is trivial. So even though it's a very powerful and general proof structure and theorem, it's actually very simple to prove. But the way to go from lines to curves is to say I have the optimal line and I'm going to form a curve by essentially splitting time into epochs, and I'm going to get I'm going to choose a different line in each epoch, and then I'm going to stitch those lines together to get a curve. So essentially I want to get these kind of curve crossing inequalities, and I'm going to just approximate my curve by different lines. And so you should just think of eta as being a tuning parameter like 2. So I split my time into epochs like 2 to the power 1, 2 squared, 2 cubed and so on. And in these geometrically spaced epochs, I kind of fit a different line in each of those epochs. And I have an error probability alpha that I'm allowed to spend, and I just spend it over time like a union bound. So I just pick a function that sums to 1, like 1 over k squared or something like that, and I spend alpha by k squared in the kth epoch. Okay, so I pick a different line with crossing probability alpha by k squared, and then I can actually just tune that to get a curve. And so this is an example for what you get in the sub-Gaussian case. Okay, so let's say I have a one sub-Gaussian random variable with zero mean. If you have sigma I, you can amend all of this. I'm writing this for simplicity. We take, instead of 1 over k squared, we take 1 over k to the power 1.4. That s over there is 1.4, whatever. You can take squared if you want to, and we take eta as 2. This is, and then you get this kind of interesting closed form expression, and it says the probability that there exists any n such that my sample sum exceeds something that looks like a non-asymptotic version of the law of the iterative logarithm is at most alpha. So it has the same behavior of square root log 1 over alpha. It behaves like square root n because these are sums and not averages. If I was to look at the average, I divide by n and it will look like 1 over root n. These are sums, so it scales like root n. And I'm paying a log n price because I want to say something simultaneous over all n. Okay, so this is a tight non-asymptotic version of the law of the iterative logarithm. This is tight in a sense that if I take my general bound, which is in terms of s and eta, and I actually send eta to 1, if I take eta to 1, I can recover the law of the iterative logarithm exactly with the right constant. So these type of non-asymptotic law of iterative logarithm inequalities can imply the asymptotic law of the iterative logarithm with exact constants. We even have a matrix law of the iterative logarithm which is new with the upper lil. You get upper bound, upper law of the iterative logarithms from this. And if you look at the like how does this perform in practice, this sub-Gaussian case was very well studied. Actually, it goes back to Darling and Robbins in their original work. Somehow, in the bandit literature, they kind of reinvented the sub-Gaussian case, but got worse bounds than Darling and Robbins. So I think people should just go back and read the literature better. But finally, I think our bounds can actually beat Darling and Robbins. It's just Darling and Robbins did not have the right line and didn't use the right stitching method. But modulo that, because we have the optimal line and a nice way to stitch, we actually get tighter, empirically tighter bounds. And so if you want to look at the difference to a point-wise, these are confidence sequences, so they're uniformly valid. That's a point-wise Hooftings bound. Okay, so it's going to be usually about 1.5 times wider, and maybe like compared to a CLT about 2 times wider. The reason it has that behavior is because I have this log n, and I want it to be really tight asymptotically when n is large. But somehow if I want something that's good in finite samples, I can pay a much smaller price relative to CLT. I can actually pay something like 1.4 times CLT. These are, anyway, they are minor points, but at least the broader point is you really get small and practical constants out of this, and you get tight confidence sequences. Yeah.
Just a very quick question. So the line that you pick, of course, will depend on x. I mean, x, I think we have some ideas in general of how to pick x, but you also...
What is what do you mean by x?
You have these lines as a function.
Yeah.
Small x and small m.
Yeah.
Right?
So we have actually.
What is the rule of? I was trying to.
Yeah. So actually, our theorem has we have 4 ways of writing the theorem, because our line can be parameterized in many ways. One is it passes through the point x comma m, and I want to find the best line. So I can ask the question: given that a line passes through x comma m, what's the line that minimizes the crossing probability? And so the line that we have minimizes the crossing probability across all lines that pass through x comma m. But I can also say I have a particular intercept, like what is the slope of the line that across all lines that has a particular crossing. So I can parameterize this in many ways. So it turns out what I'm doing in this particular case is I'm taking the geometric midpoint of these guys, and I'm saying I want it to pass through the I want it to be tight. I want a line that's tight at the geometric midpoint, and I want it to have this particular crossing probability. So somehow when you fix x and m, the crossing probability is determined by x and m. So the 3 things are tied, x, m, and alpha. So, but you can fix any 2, and the third one is determined by the other 2. So what I'm fixing is saying I want this to be alpha by 1 proportional to alpha by 1 squared. I mean, there's a 6 by pi squared there. So anyway, I want it to be like alpha by k squared. I fix that, and I fix the point, which is the geometric midpoint, on this axis that I wanted to pass through, and then the line where it crosses on this axis, the x is determined automatically. So there's only one line that has those 2 features. So
yeah, I was also wondering if you have an intuitive interpretation for what m is. I think that was what. I guess with alpha and x, it's very like you said, x is like the line. X corresponds to.
No, it's x comma m. Like it's a line that passes through the point x comma m. So there's many lines that pass through x comma m, and one of those lines minimizes the crossing probability. So if I change this line, then like it's going to have a lot. The probability of this random walk crossing that line is going to be more, and so this particular line minimizes that crossing probability. So it's just that you have to parameterize a line, and so in this case it's a line that passes through the point x comma m, and then the slope is chosen to minimize the crossing probability. So but you can parameterize, as I said, there's 3 things. A line needs 2 parts, and then the crossing probability. So like the line and the crossing probability are 3 things. You can fix any 2 and determine the other one. But I presented one way of writing down the bound. It turns out that it also strengthens what are called self-normalized concentration inequalities. If you've heard of self-normalized concentration inequalities, De La Peña was developing those, but like vision.
Next week, De La Peña is collecting a tutorial.
Oh wow! Okay,
Next week.
Interesting. I don't know if he'll talk about this particular stuff, but anyway, a self-normalized concentration inequality has this. It works differently, but it looks like Sn by Vn and Vn and so De La Peña proved a lot of inequalities of the type that if Sn by Vn is the probability that this ever exceeds x and Vn ever exceeds m is exponentially small in x comma m, so some function of x comma m, And so what this corresponds to in a plot of this kind is that he's basically saying that after time m, the probability that it ever crosses level x. So his line looks like this. Okay, and it's very interesting because Friedman inequalities say something before time m, and De La Peña's inequalities say something after time m. But it's our bounds don't have any restriction on time m, and if you look at what our bound says on this scale, it actually gives a bound like this. So theorem 1 looks like this. So if I just divide throughout by Vn and write it as Sn by Vn in our bound, then what was a line now looks like a 1 over that curve, and that curve is uniformly better than this. It says something non-trivial across all times, and it's uniformly better than De La Peña statements after time m. So it's quite interesting because it unifies Friedman type inequalities and De La Peña type inequalities. So like they seem to be these self-normalized inequalities, because you're dividing by Vn, it seems like you need to have Vn be large, otherwise you have issues of blowing up near 0. That's why they were introducing these things. But it turns out Friedman style and De La Peña style, they're the same style, they're the same inequalities, and once you write it down as our theorem, you improve both of them and unify both of them, because they're like different literature. Self-normalized inequalities are one literature, and these type of Chernoff tail bounds are another literature. Actually, they're all doing the same thing. And the one way of deriving all of them is write down a super martingale, apply Wheel's inequality, tune lambda, and you can improve all of these bounds in literature. So it's very clean, unified, and simple.
Quick question.
Yeah.
So the way in which you're constructing this stitching sequence, you already described it nicely, which is that I pick the midpoint, I make
geometric midpoint, yeah.
Yeah, and then I make sure I pass through a fixed point. But in principle, is this even reasonable that I construct the stitching sequence based on my process in the beginning of my epoch? So that somehow the intercept can...
Yeah, the intercept actually is determined because I fix this x-axis and I fix the alpha. So the intercept is determined by those two, the optimal line. So it's a full line actually, I just ignore it in other parts, but I get a line that's determined by eta to the power 1.5 and by alpha by k squared. So I that determines the line.
I was asking a slightly different question.
Yeah.
But if you chose to parameterize slightly differently,
Yeah.
so if at the end of epoch 1, if the process is small,
Yeah.
in principle my intercept can shift.
Yeah. No, but that is determined because actually I've written this as n, but it's actually Vn.
Oh.
And so I'm actually not looking up to time n. I'm looking up to intrinsic time n, and that's actually very important. It's very important. I should switch in intrinsic time scale. The actual process, the real n doesn't matter. If I pick up variance slowly, I'm still in the first epoch essentially, or something like that. So it's really intrinsic. The stitching happens in intrinsic time. Yeah, it's a subtle point, but that's the right way to do so. That's another reason we're able to improve bounds in the literature, is because some bounds stitch according to n, but you should be splitting time up according to intrinsic time. Yeah. Anyway, yeah. So more generally, like I showed you this, but if you want to estimate, I said you have these crossing boundaries, but here's a confidence sequence. Okay, so if you have a coin and you're tossing it and you want to estimate its bias over time, then this is a confidence sequence for the bias. So think of Sn as being -1 for tails and +1 for heads or something like that. So that's the sum of the coin tosses so far. That's the empirical mean. And then I have this eta and h function. Eta is 2. H is like 1 over k squared type of function. So, but you get this. You can get a variety of boundaries, but they're very clean and closed form. But you get a confidence sequence for the bias just through these kind of time uniform crossing boundaries. There's nothing about means that's anything particular. You can do this for quantiles. So an example is for so if I want to cover the median, so I want a confidence sequence for the median, and q of half I'm calling the median, that's a quantile function. I take the empirical quantile function at half plus ut and the empirical quantile function at half minus ut. And what does ut look like? Just some small constants like log t, log 1 over alpha by square root t, and this is a confidence sequence for quantiles. Okay, so you can track quantiles if you want any this is I've done it for the median, but we have an expression for any quantile, and you can actually do all quantiles simultaneously. So I call this a time uniform DKW bound. If you know what to do, DKW is it's a fixed sample Hoeffding bound for the CDF, but now you can do the same thing. So for all quantile levels and all time simultaneously, the quantile at level p is bounded by the quantile at level p plus ut and p minus ut, where ut is very small and simple and clean. It's a very, very small expression. So visually what this means is, like, so for example, if you have a Cauchy distribution let's say I'm looking at the 90% quantile of a Cauchy distribution, then the empirical quantile, the empirical 0.9 quantile is this dotted quantity, and the true 90% quantile is this gray bar, and then this green bands are telling you our confidence sequence for that 90% quantile, and they shrink at a square root log t over t rate. And this is for the whole CDF. So you can say, well, I don't want just a particular quantile, I want the entire CDF. This is the CDF of a Cauchy. The dotted line is the empirical CDF of the Cauchy, and those bands are the confidence sequence for that empirical CDF over time. So as you get more samples, obviously the empirical CDF, the confidence band tightens and so on. So you can track these kinds of empirical CDFs on the fly. You can, nothing related to univariate, you can do like covariance, sequential covariance matrix estimation. So you can get these operator norm bounds on the covariance matrix that hold simultaneously over all time. The only difference with respect to a fixed time bound is a log n in the, that's the only difference with respect to a fixed time bound. And so like if you have, you can visualize covariance matrices as ellipses. So in this case I have a 2-dimensional one, so you can visualize it. And so after 200 samples, your bound on the covariance matrix looks like this. That's the blue one is the true sigma, and our bounds look like this in operator norm. After some more samples you get a hole, and then after some more samples you get a tight bound. So you can track your covariance matrix online over time and stop whenever you want, and you can do sequential tests for covariance matrices and things of that kind. Okay, so you should think of our bounds as being non-asymptotic versions of the law of the logarithm. They are non-parametric generalizations of the SPRT, and they are time uniform extensions of Kramer-Chernoff inequalities. That's how it's kind of connected to the literature. And at a high level, this is all we did. If you missed some of it, we construct an E-process. If you apply Wheel's inequality, you get a tail bound in terms of this lambda, these bets, and then you optimize lambda via Chernoff trick, you get a line crossing inequality. Instead, if you mix over lambda, you should think of this stitching as being a particular form of a mixture. You get a mixture super martingale. Now you apply Wheel's inequality, you get a curve crossing inequality instead. And so, so Wheel's can be applied before or after mixing, and in one case you get line or curve crossing inequality. So this is basically what I just presented to you. And so what we have is basically new mixtures in new non-parametric, new E-processes, new mixtures that give you closed form confidence sequences that have either square root t log t growth or square root t log t growth. And there's some kind of they don't uniformly outperform each other. Like these are asymptotically the right rate, but in smaller samples do worse. These ones are tighter in smaller samples, but asymptotically do worse. But they both actually don't uniformly dominate each other. But you can get boundaries or confidence sequences that feel like either of those. And they're very practical. It turns out that the state-of-the-art election audits are now based on our betting methods for sampling without replacement. They're actually being launched in the coming elections in a pilot and stuff like that. So that's joint work with Philip Stark. And then you can use all of this to all confidence sequences to do A/B testing and to find confidence sequences for the average treatment effect, things like that. And now they're actually being used by Amazon and Netflix in public-facing software. So actually, if you Google Netflix, if you Google for Netflix had a blog post a month ago which was titled "Sequential A/B Tests Keep Netflix Streaming." This was a blog post that they wrote, and in that blog post they directly cite and say these uniform quantile bounds that I presented, that's exactly what they use in Netflix. Every change that's made by a Netflix engineer goes through canary testing based on our confidence sequences, and if it passes those and shows things work fine, then it's launched. And so they describe in that blog post how they use these confidence sequences in practice. And you can adapt this to more complex settings involving bandits and contextual bandits and stuff like that. And at Adobe and Microsoft, again, they're already being deployed in public-facing software in those contexts. Okay, so I'm at 12. That's all I have for the moment. Let me stop there. I'm happy to stay on and take more questions. But for those of you who need to leave, thanks for staying and thanks for your attention.